Here's problem number 31 from section 4.1. We're asked to find the extreme values of the function on the interval where they occur. And of course, since we're given an interval, and in this case the interval is from -5 to +5, because that's a closed interval, we know that we should be able to find absolute maximum, absolute minimum, as long as this function is continuous, and it is on that interval. So let's see what we can do about finding those local maxes and local mins. Now, there's two ways that I can handle this problem. One way would be, let's look at the graph. And if we look at the graph of this function, now this is just using the standard window. So let me set the window to match the limitations that the interval that we're interested in. And if I graph that, and it looks like maybe I need a little bit more y, so let me adjust my y. Don't need so much there, so let's go from -5 to 15. So if we do that, it looks as though we've got an absolute minimum down here, and then one of these two endpoints, and it looks like this one is going to be the absolute maximum. This one over here, a local maximum. And we could go ahead and calculate that out. We could say f of -5, which is the absolute value of -5 minus 2, plus -5 plus 3, which is equal to the absolute of -7 plus the absolute of -2, which is equal to 7 plus 2, or 9. That, again, according to our graph here, looks to be a local max. It looks along this long stretch like at 0, we're going to end up with the absolute of -2 plus the absolute of 3, and that looks to me like that's going to be 2 plus 3, or is equal to 5. And then it looks like on the other end at f of equals 5, I could do this work, but why not I just go over to here and say trace, and then put in when x is 5, and I get y is 11. And again, that looks to be an absolute max, which is also a local max. Alright, over here, a local minimum. Now, that's great. We got the calculator, and it helped us out immensely. But there's something a little bit unsatisfying here, and that is, why does that graph look like that? And maybe this is worthy just of a little bit of exploration about the nature of these piecewise functions. An absolute is a piecewise function. If we remember that the absolute value of x is equal to either -x when x is less than 0, or plain old x when x is greater than or equal to 0, we begin to think of this function as what happens when we cross the threshold when x where the expression x minus 2 becomes 0, or when the expression x minus 3 becomes 0. And so we think of this as a piecewise function, and that piecewise function is going to be the first set of values is going to be while x is less than -3. Why -3? Because that's the place where this particular expression crosses the threshold of 0. And when we do that, values of inside here are negative, so we essentially end up with the opposite of x minus 2, plus expressions in here are going to be negative, so we end up with the opposite of x plus 3. And if I clean that up, this ends up being a -x plus a -x, or a -2x, and this is end up being a +2 and a -3, a positive 2 and a negative 3 ends up being a negative 1. And you can see that this function does look like it has a negative 2 slope there. Now, when we're between negative 3 and 2, why 2 again? Because that's the thing that makes that. This second function is negative, but the first function is negative, but the second function gives positive value, so we just get an x plus 3. And when we get that, we got a negative x and a positive x. Those two cancel, and then we end up with a negative 2, opposite of a negative 2 plus 3, and that's the thing that gives us that 5 that runs all along there. And then lastly, when x is greater than 2, this ends up being x minus 2 plus x plus 3, or it gives us the function 2x plus 1. And you can see that this looks very much like a 2x plus 1 function. Why is this whole thing, why is there a local minimum here? Well, if we take this and translate that piecewise function into a derivative function, we get a negative 2 derivative when x is less than negative 3. We get a 0 for the derivative when x is between negative 3 and 2, and we get a positive 2 slope when x is greater than 2. And because these things meet at corners, you're going to note that I don't use the equal to sign on any of those. And so that's a pretty long-winded discussion about problem number 31.